My name is Doris, and today I'll be talking about how you can scale your pandas workflows with Modin. And as a brief background of myself, I've been working in the Python data space largely for the last decade or so. It all started, when I was doing astrophysics research, and I was working with large amounts of data, cosmological data. And at that time, I picked up Python and pandas and Jupyter and all the good tools in the Python data ecosystem. And it became really clear to me, when I was about to go to grad school, I was like, hey, look, there's all these incredible open source tooling in the Python data ecosystem, and it's really helping us accelerate the scientific research that we were doing. And so I was so inspired by seeing all of these open source tooling that for my PhD, I actually decided to focus my work on building tools to help people better understand, visualize, and explore their data. So a lot of my early PhD work was focused around working with domain scientists, largely in astronomy, genetics, material science, and kind of taking this human-centered approach in designing data science tools and systems. And some of the work that I'll be talking about today started during that time. As we were doing, I was at UC Berkeley doing this research, we developed a couple open source tools along these lines. And then after Berkeley, I started with a few of my lab mates a company called Ponder, which is centered around the mission of how do we improve data science productivity by empowering people to work with data at all scales. And you'll hear a lot about that in my talk today. And last year, Ponder was acquired by Snowflake, so I'm now working at Snowflake to continue this line of work in the open source and also bring our best-in-class Python experiences to Snowflake. So we're at SciPy today, so most of you have probably heard of or used or even contributed to pandas. But just as a recap, pandas is a tremendously popular Python library for data transformation, pre-processing, feature engineering, analysis, and so on. And pandas lets you work with data frames, so you can think of these as tables essentially, but it comes with these convenient APIs for helping you load, clean, transform, and analyze your data. And so over the past couple years, we've worked with a variety of data teams and organizations who are using pandas sort of in an enterprise or a company sort of context. And one of the things that we observe is that data teams love pandas because it's really flexible, it's expressive, it's easy to do these quick prototyping and experimentation. It's also very intuitive and easy to use. And because it's open source, it's been around since 2008, it has a growing community of users, and it's widely adopted. In fact, if you go to any data science training or bootcamp, if you take any intro to Python courses, pandas is almost for sure part of the curriculum. So it's virtually used in all sectors. We've seen this in biotech, finance, manufacturing, and so on. Basically anywhere where you're using and working with your data with Python, you're using pandas some way or form. So we know that pandas is great, but one of the biggest challenges that we hear from users is that even though pandas works really well on small sort of clean toy data sets, it often breaks when you are looking at the scale of real world data. It's single threaded, so things can get really slow when you're operating on large data sets. And what's even worse is that because pandas is an in-memory data structure, you can only work on data that fits in memory. And so the moment you exceed that, you start running into these out-of-memory issues. And so this leads to a really frustrating development experience, especially as you're working with larger data sets for individual developers. And so next, I kind of want to illustrate how these challenges sort of extends into the impact that it has on data teams and organizations. So as I mentioned, many organizations are using pandas for this initial sort of data exploration, prototyping, as new business requirements or new data comes in. And so this is the area that pandas really shines. And so most of this prototyping work in pandas, we often see people are doing this on their laptops or in a single sort of shared cluster machine that the data teams are using to quickly test and prototype or experiment in a very agile way. However, the trouble is that the moment you need to look at more data, maybe you're testing or productionizing on a larger sample of data, this picture starts to break down, right? So the tool that you're using for this initial stage doesn't scale. And so what happens is that to work around these limitations, data teams are forced to rewrite their pandas workflows into a big data framework. And we often see this being Spark or SQL or another type of big data tool as they're moving these workloads to the cloud to run on larger data sets. And so when we go from prototyping to production, this becomes now a really time-consuming process of constantly having to rewrite these workflows into these scalable frameworks. And so as an anecdote of one of the data teams that we've been working with, they told us that it took over 6 months for them to translate one of their pandas workloads into Spark, just to be able to operate on more data in production. So this really leads to precious developer time being wasted. So the story doesn't end here, right? We all know that when you're developing a data science workflow or a machine learning pipeline, you have to iterate. You have to, change your parameters, changing things as new data comes in. So even if you've gotten to this point where you've rewritten your initial workloads in a more scalable way, things can break in production, bugs can get introduced, and you're kind of in this cycle of having to constantly rewrite. And so the rewriting isn't a constant one-time cost, but there's an overhead as you're maintaining and debugging your workflows, which leads to overall a longer feedback cycle and development time. So what I hope you take away from this slide is that all of these points of friction of having to rewrite your pandas code just to be able to work with more data starts to add up in terms of human time and development cost, and it becomes a really big challenge. So I often have this meme which kind of summarizes this challenge that a lot of data teams, data scientists have to deal with when they're thinking about working with pandas at scale. So, we started off developing Modin really based on some of these observations that we saw, across data teams. And to address some of these challenges, we've been working on an open source project called Modin. So you can think of Modin as a faster, more scalable version of pandas. So with Modin, you can see on the right-hand side here, all you have to do is change a single line of import. And now you can work with much larger data sets with the operations running in parallel. So Modin is an actively maintained open source project that's based off of some of the research that we were doing at UC Berkeley on adapting databases and distributed computing techniques to pandas. And so going back to the picture that I showed earlier, Modin sort of solves this scalability challenge that we discussed earlier by saying, hey, across your prototyping to production, you can continue to use the same consistent API that you've been using, namely with pandas, throughout the life cycle of your entire project. And so as a quick demo of how Modin works in action, here I have 2 videos side by side of Modin and pandas. The text is a little bit small, but essentially it's the same code with the import being different. And I'm going to start running this. And you can see that as I'm running this is around 2 gigabytes of New York taxi data set. And this is all running. It was running on my laptop. I took these videos. And so the queries are all the same. But we could see that Modin finished much faster than compared to pandas. And if you plot the runtime, you can actually see that Modin on average is able to get several x faster than pandas, even just running on my laptop without having to change any code. So this is the kind of the performance improvement that you get just out of the box for these different functions that I tested here. So a little bit deeper into now we've taken a look at the demo, how does Modin actually work underneath the hood? Why is Modin able to run much faster in the demo that we showed earlier? So as I mentioned earlier, pandas is single threaded, right? So that means that even if you had 4 cores, 8 cores, a really large machine that you're throwing at it, it's not able to fully utilize the resources that are available. And so in contrast, Modin runs your data frame operations in parallel so that you can fully utilize the compute resources that are available on your machine to speed up performance. And in fact, the more cores you throw at it, the better, because it even works on data sets where you can't even process that in memory with pandas. So beyond your local machines, Modin even works in a cluster setting. So in some of our research papers in the past, we've ran benchmarks comparing Modin with respect to other parallel data frame implementations. And you can see that Modin's performance come out ahead, leading to orders of magnitude speed up across common sort of pandas operations from read CSV, fill NA, group by, and so on. And so, as I mentioned earlier, like one of the reasons why people love pandas is the very flexible sort of expressive API that it comes with. So pandas has like something like close to 600 plus APIs and so on, covering almost everything that you can imagine doing with your data. But that's a lot of APIs to cover, especially as you are thinking about a scalable data frame and having to re-implement every single one of them. Naively, like what I would do is, hey, I would take one of those APIs, I would try to scale it up, and I would have to do that 600 times. So that's a very expensive effort, and in our experience, that technique doesn't really work very well. Because of how much of the breadth of the APIs that we have to cover. So instead, what we actually did was that one of our secret sauces, we actually started from first principles. We looked at all the pandas sort of operations, and we defined an algebra. We defined a data frame algebra in one of our past research papers, and we essentially are able to map this broad 600 plus APIs down to that algebra. So then we can implement the algebra and sort of apply that onto the underlying engine. And so if you want to learn more about our research on data frame algebras and how we did this with Modin, you can definitely go check out this VLDB paper that we wrote a few years ago. So you also notice that in this architecture diagram, we have pandas API on the top. We're compiling it down to this intermediary algebra. And then at the bottom, there are different open source sort of backends. So Modin supports different open source backends, including Ray and Dask. And the latest addition to this is our Snowflake backend. So I'm going to talk a little bit about the newest release around how Modin runs on Snowflake. So we recently launched this Modin on Snowflake. We're calling this Snowpark Pandas API. So it's part of our ongoing effort in Snowflake with the Snowpark project, aimed at being able to support developers to run Python code within Snowflake. This means that you can work with your data in Snowflake without the need of having to write any SQL. You can, all of you are at SciPy, you love Python, and so you can continue to write Python, and then, still work with the data in Snowflake. So with this new Snowpark Pandas API, you can additionally also use the Pandas API for flexible data transformation. So what's happening here is that when you're writing Pandas, the Snowpark Pandas API, the compute gets pushed down to run on Snowflake so that you benefit from many of the things that you get with using Snowflake. You don't need to manage or tune your compute infrastructure to get the massive scalability benefits with Snowflake. Your data also never leaves the warehouse. So in contrast to when you're usually working with pandas, you often have to pull your data out of your data warehouse or out of a database to be able to operate it in memory. Your data doesn't have to leave. Because we're pushing down the computation to Snowflake, you inherit a lot of the security and governance benefits that are backed by Snowflake. So this is a glimpse of like how we're doing this underneath the hood. So here, the user is writing some sort of pandas query, in this case, like let's say pd.concat. I'm taking two data frames, and I want to concatenate them horizontally. We essentially compile this query down to SQL so that it's running on the underlying Snowflake SQL engine. And so the kind of the big picture here is that the user is writing some sort of Python and Pandas code, and Snowflake handles this magic of transpiling it down and running it in the Snowflake backend. And so if you're interested in learning more about this Modin on Snowflake implementation and how you can use that, definitely check out this QR code to learn more in our documentation. So this is kind of a summary slide, but in summary, Modin is an open source library that helps you seamlessly scale up your pandas workflows by just changing a single line of code. If you want to learn more or check out some cool demos, make sure you come by the Streamlit booth during SciPy. We'll have Modin developers as well as our community members there to share more. You can ask questions. And then we also have some really cool Modin stickers, which is designed exclusively for SciPy. So make sure you drop by to pick up some of those stickers. And so with that, thank you for listening. I have some QR codes up there on some related resources that you might want to check out. But with that, I'm happy to take any questions. Thank you.
Thank you very much, Doris. Hang on one sec. Let me see if there are any questions in the Slack channel. Wait a moment. Okay, hang on a minute. So here's one, hang on a minute. Here's one from Benoit. When I started using Dask data frames, the API made every effort to emulate the Pandas API, but had to leave out some features that were tricky to implement in a distributed computing framework. Does Modin have the same sort of restrictions driven by calculation distribution, or is there magic to work around them?
Yeah, that's actually a really great point. So one of the key differences between like Modin and other scalable pandas sort of implementations is that we try to mimic sort of what the pandas API supports. And so going back to kind of the algebra work that we talked about earlier, this is one of the reasons why we're able to support such a high coverage of the pandas API, because we have this underlying like algebraic implementation. There's about like 13 or so core operators. It allows us to support like a broader set instead of having to implement the pandas API one by one and scaling that up. So that's one of the key differences between Dask data frames. In fact, we use Dask underneath the hood as a scheduler to distribute our computation. But we also do see that a lot of data frame libraries, scalable data frame libraries specifically, having that limitations of having to rewrite. And so the design philosophy has always been like stay true to what Pandas API has been doing.
All right, thank you. Okay, I'm not seeing any more in the chat. Are there any questions from folks here in the room? Yeah, hang on Oh, you did. Okay, hang on. Let's take a look. I'm not seeing it here in Slack, sorry. Sorry? Oh, it's in the thread. I'm not seeing it in the thread. Oh my goodness. Yeah, why don't we do that since you're here? Thank you very much.
Thank you. Yeah, so my question was essentially, is the usage of Modin or Dask a choice of one or the other? I haven't used either of these, so I'm not too sure. But if Dask is used under the hood, then is there ever a situation where we wouldn't want to use Modin? And then kind of similarly to that, should we always use Modin if we're using pandas?
Yeah, that's a great point. So as you can see, like with Modin, we allow users to kind of flexibly sort of pick their own backend. By default, if you just like do pip install Modin and you start using Modin, we actually have Ray as the default backend. Both Ray and Dask have been like, Ray, Dask, and then our new Snowflake backend have been like well tested, and essentially users can configure their own backend, so you can set your backend as Dask. We oftentimes see that people want to set their own backend if they already have existing workloads that are running, let's say, in Dask or in Ray or in Snowflake and things like that. So it really depends on like what your overall sort of data architecture is like today, and then we try to kind of integrate closely to that. In terms of like the differences between why you would use Modin or why you would use Dask, Dask is an amazing sort of parallel sort of Python library. It's great for like, what we're doing here, which is scheduling, task distribution, and things like that. But the goal of Modin is really staying true to the Pandas API. So like it's really designed for developers who are living and breathing the Pandas API. But if you want that like extra flexibility, you have like ML training and workloads and things that you want to like develop, maybe like Dask or Ray or some of the more underlying engine would be a better option. So it really depends on where, what kind of workload you're doing, whether it's like Panda centric or is it something else.
All right, thank you. Are there any other questions in the audience here? Oh, hang on one sec.
Yep. Hi, I had a quick question. So you mentioned like Modin is backed by Dask engine, and that works for a single instance with multiple core, right? Like I don't have to do anything and it'll handle that itself. Is there any configuration settings on how to go about it when you are actually doing processing on distributed systems where there are like multiple instances, and how do I go about it? Like, are there any benefits? Are there any recommendations as such?
Yeah, so with when you're just like installing Modin and then you start writing a Pandas data frame command, will automatically like initialize like a Ray or a Dask cluster based on like what you've picked. So that's kind of the single node setting. And then obviously there are like, as you're going to a cluster setting, you can configure like multi-node setup. Both Ray and Dask support those use cases. And our documentation actually has a, kind of a best practices guide on in terms of like, what are some of the configurations or settings that you need to do to work on those multi-node use cases.
Oh, hang on, one more over here. Oh, he's meeting me halfway, thank you.
It's a little exercise. Hi, Gordon Watts from University of Washington. Great talk. I wanted to ask a little something about the algebra. So if I have a sequence of pandas operations, does that get translated into a sequence of these lower level algebraic operations? And if so, is that something one can then reason about, potentially optimize, as opposed to just eagerly of doing each single pandas API individually?
Yeah, definitely. That's a really good point. So one of the part of what we've done in terms of our research is if you're doing like, let's say a lot of chaining or like a workflow of Pandas operations, there are like lazy evaluation strategies that we are employing to make sure that, we can fuse certain operations or optimize it in certain ways. But Modin is kind of operating in this interesting realm where Pandas is like fully eager, right? So you're doing like a df.groupby.sum, it just like executes. Modin understands that, hey, like Pandas developers are operating in an interactive manner, so they want to like look at previews, print out like their df and things like that. So we kind of operate in this like interesting realm of like a little bit of eager, a little bit of lazy to mimic sort of the Pandas behavior, but also taking advantage of some of the lazy evaluations so that we can optimize those workloads.
Okay, any more questions? The Slack channel still seems to be silent. Okay, well, I think we're a couple of minutes till the next session. So why don't we thank our speaker one last time? So thank you, Doris.